Okay, thanks for the opportunity to talk about something that's been of interest to me for a long time. What I thought I'd do is start with the largest part of the mantle, which we think is adiabatic, and I'll explore that idea of adiabaticity and some of the assumptions behind it and where those assumptions might go wrong. I'll then talk about melting as a primary constraint on the geotherm, and I'll take a brief peek into the past. Jackie mentioned evolution of the Earth and the time variation of the geotherm. I'll say a little bit about that. I'll then look at the upper thermal boundary layer, the lower thermal boundary layer, and a little bit about the core at the end. Okay, so the idea of an adiabat. So an adiabat is a line of constant entropy in temperature pressure space or temperature depth space. So all of these red lines are isopleths of entropy, right? And so the entropy is constant along each one of those lines. The temperature increases with depth because of adiabatic heating. If you compress something and it doesn't lose heat, its temperature will increase, and that's what's going on here. Just that very simple physical effect. It's conventional to, even though these are lines of constant entropy, it's conventional not to label them by the entropy that they correspond to, which would be something like 2.5 joules per gram per Kelvin. You know, we don't usually think about units of entropy. Instead, it's conventional to label them by the temperature that they have at the surface. And so you have several different isopleths of entropy, each one we can think of as being labeled by the temperature of the surface, going from 1,000 Kelvin, adiabat potential temperature of 1,000 Kelvin to a potential temperature of 2,000 Kelvin. And this is something like the variability that we might expect in the convecting mantle. Thorne, in his talk yesterday on deep earthquakes and subducting slabs, highlighted the 600 degree C isotherm. That's about 900 K, close to 1,000 K. So the core of the slab is going to be something like this. A plume might be something like this, and I'll argue later that sort of a mid-ocean ridge is somewhere in the middle, more or less. Okay, so a couple interesting things to note is that these curves fan out as you go down in depth. And the reason for that is very simple. If you look at the thermodynamic identity for the variation of temperature with pressure along an adiabat, it's equal to gamma, which is the Gruneisen parameter, dimensionless quantity, which has a value of about 1.5 over much of the Earth. The temperature itself appears again, and in the bottom is the adiabatic bulk modulus. And it's kind of nice that appears because that's something you can measure seismologically. And indeed, many people have used that relationship to derive geotherms. These particular geotherms here are computed by Hephaestus, which is our thermodynamic code, which I might have a chance to say something more about tomorrow. I won't get into the details of it here. Anyway, so the reason that the adiabats fan out as you go down in depth is because temperature appears in the expression for the gradient, okay? The bigger the initial temperature is, the bigger the gradient is, and so you get this fanning out. Okay, so that has some interesting implications. For example, if you have a plume, right, that you infer to have a potential temperature that's 400 degrees hotter than normal mantle, say, if it's 400 degrees hotter near the surface, it's going to be much, much hotter than that at the core mantle boundary, about 70% hotter. So it might be 700 degrees hotter than normal mantle by the time you get to the bottom of the mantle. So the actual origin of the plume at the core mantle boundary might be 700 degrees hotter. By the time it gets to the surface, it's only 400 degrees hotter. In detail, you can understand the tendency of these guys to have curvature like this for the slope to decrease, and that's just because the adiabatic bulk modulus increases faster with depth than the temperature does. The other thing that shows up here are these wiggles. These wiggles are due to phase transformations, and this is due to the exchange of latent heat at phase transformations. You can have exothermic ones on descent or endothermic ones, exothermic ones on descent, will lead to positive upticks in the adiabatic temperature, and endothermic ones will lead to little negative down ticks. This was first recognized by Verhoeven in the 60s. And this is a way of illustrating that relationship. What I've done here is to include a representation of all the phases, phase assemblages that are stable in a pyrolite composition, and I plotted the 1600 Kelvin adiabat on top of it, and you can see that these jumps correspond to phase transformations. This is just the upper 30 GPa that I've represented here. Okay, so adiabats. Let me take a step back. Okay, why did we talk about adiabats? Is there any actual reason to believe that the mantle is adiabatic? I mean, there are theoretical reasons to believe it. It's based on a very simple idea that in a convecting system, upwellings and downwellings don't exchange heat with each other. But is there an observational basis for it? And the answer is yes, at least over portions of the mantle. And it's based on this thing called the Bullen inhomogeneity parameter, which is the ratio of the seismic parameter divided by rho g, and then multiplied by the density gradient in the Earth. Okay? So from a combination of body waves and normal modes, you can determine the depth variation of seismic wave velocities, which gives you the seismic parameter, and the depth variation of the density. Okay? And another way to think of this is that the Bullen inhomogeneity parameter is the ratio of the adiabatic bulk modulus measured seismologically at very high frequencies to the bulk modulus that gives you the density pressure relation that you have in the Earth. You can think of that as the equilibrium bulk modulus versus the unrelaxed bulk modulus. Okay? And in portions of the mantle that are homogeneous, not undergoing phase transformations, and adiabatic, you expect this thing should be 1. And indeed, throughout most of the lower mantle, this parameter is indeed 1. This is from Prem. Now, you have to be a little bit careful because you can probably change this guy. The density distribution is the least well constrained of all of the depth profiles in Prem. Seismic wave velocities are much better constrained than density. You could probably change this guy by a few percent up or down, and that can be significant in terms of deviations from adiabatic behavior. I'll show an example of that in a second. But just to point out that there is some observational basis for the notion of an adiabat, at least in the lower mantle. One of the things that Jackie mentioned, this was first recognized by Dan McKenzie in the 70s and kind of gets rediscovered every decade, is that if you have internal heating, you actually don't expect the mantle to be adiabatic. You expect the temperature distribution to be subadiabatic. That is, for the temperature to vary less with depth than an adiabat. And this is just one illustration of this effect. This is from convection calculations by Peter Bunge and others. And what they're showing here is the temperature variation with the adiabat subtracted out. Okay, so this means that temperature is varying less rapidly with depth than an adiabat, and these different calculations are for different amounts of heating from below. So this one is purely heated from within. This one is, I don't know, some fraction of heating from below, maybe half and half, something like that, and then everything in between. And you can see that the temperature gradients are indeed subadiabatic in all these cases, and this can cause deviations from the adiabat of a couple hundred degrees, something like that. So that's a deviation from the adiabat that we might expect to occur. Another deviation from the adiabats that I showed you is if there's any degree of dynamical layering in the Earth. And indeed, we might expect this to occur. The negative Clapeyron slope associated with the perovskite forming reaction may indeed impede mass flow across 660 kilometers. There may be other parts of the Earth that have similar effects that we don't know about yet. This is one example of a convection calculation where this negative Clapeyron slope has been included. And what it shows is that if there is an inhibition to mass flux across 660, what happens, this is a temperature field here, what happens is that the lower mantle tends to be heated up compared to the upper mantle. Okay, so this would cause the AdBat to kind of jump up at 660 by a few hundred degrees, something like that. So the lower mantle would be just sort of intrinsically hotter, higher potential temperature than the upper mantle. So this is something to keep in mind as well. We've already heard over the past few days of evidence in tomography of slabs flattening out at 660. Maybe eventually they dive down into the lower mantle. But there does seem to be good evidence in tomography that there's at least some inhibition to mass flux at 660. Probably not perfect layering, but some inhibition to mass flux. And you would expect then some increase in potential temperature as you cross the 660. Okay, so coming back to AdBats, which, I've given you some of the assumptions, I've given you some of the reasons to question the idea of an AdBat. Nevertheless, I think it's still a useful idealization, an end member, if you will, to sort of think about temperature variation in the Earth, or at least a starting point for thinking about it. One question you might ask is which one? Which one would you take as being representative of the mantle? As Jackie pointed out, obviously temperature is an inherently three-dimensional thing. Very different from seismic structure. Seismic structure, lateral variations are a few percent. Lateral temperature variations, though, are much closer to 100%. So temperature is inherently 3D in a way that seismic structure is just not. So nevertheless, we can ask, if we were going to take one AdBat that's representative of the Earth, which one would you take? What I would argue is that one possible choice would be the AdBat under the mid-ocean ridge. And the reason for that is that we have a pretty good constraint on what the potential temperature is there. Probably better constraint than we do anywhere else, and that's because of the melting process. And this has been recognized for some time. This is just one example of this sort of analysis where you can estimate the solidus and the liquidus of pyrolite, and you can compute AdBats. Here are some AdBats here. And as they cross into the melting region, they're deflected by the latent heat of melting, by quite a lot actually. And by following any one of these AdBats, you can compute how much melt is generated, and therefore you can calculate how thick the oceanic crust is that results. And this is the result of that crustal thickness calculation. And what you see is that if you want an oceanic crust that's something like 7 kilometers, then you want a mantle potential temperature of something like 1,300 degrees or something like 1,600 Kelvin. The details of this calculation depend on various things. It depends on knowing the solidus and liquidus. It depends on knowing the variation of entropy throughout the melting interval, and so that the details have changed over time as people do this calculation better and better. But the bottom line, that to get 6-kilometer thick oceanic crust, you need about a 1,600 Kelvin potential temperature that has survived. Melting, as Jackie mentioned, the geotherm probably has varied in the past, and melting processes have varied in the past, and melting, as you go into the past, melting and melt products continue to be, I think, have to be considered a primary constraint on what the temperature in the mantle was. And this is a figure that Jackie showed also. This is the potential temperature versus time from Claude Hertzberg and Roberta Rudnick's paper, based partly on June Korenaga's thermal model. And we have the sort of typical 1,300 to 1,350 degrees C potential temperature for today's mantle, and then increasing by a few hundred degrees over Earth's history with some, potentially interesting variations into the Archean there, and some data from melt products as you go back in past, indicating that it was probably hotter. Perhaps we... Yes. These are different versions of the Korenaga thermal model. with different assumed values of the Urey number. That's right, just for comparison to the petrologic data there. We could go back even further and past. You see this ends at 4 billion years. What about if we go all the way to 4.5 billion years? You can think about the initial temperature structure of the Earth. Constraints are much more limited, obviously, but that hasn't stopped people from speculating. What I have here is I've just assumed that the mantle is completely molten. And if you assume that it's completely molten, and you know the equation of state of liquids, which we think we know something about now, you can compute AdBats in this purely molten mantle as well, and this is an example of such a calculation. And I've also superimposed here an estimate of the solidus and liquidus, which agree very well with the Piquet et al. Experimental data that Jackie showed. And as you cool this initially molten mantle, you first start to crystallize in the middle, which is kind of interesting. And it's interesting because the subsequent evolution then may give you a fossil signature that you can see in seismology today. And various groups, including a group from last CIDR, have thought about how the crystallization products of this basal magma ocean below the initially crystallizing sort of septum might evolve to give you the unique features of LLSVPs that we see today. Okay, let me turn to the upper thermal boundary layer. So the upper thermal boundary layer, I'll focus on oceanic regions mostly. We think of that as being affected by half-space cooling. Okay, that's the simplest physical model. In detail, if you look at oceanic bathymetry, it looks like something like a plate model. Might fit bathymetry better, although it doesn't really have a physical basis. So I've stuck to the half-space cooling model here. So here's our 1600K AdBat, and these are half-space cooling lithospheres for the ages marked there in millions of years. And one interesting comparison you can make is to the solidus again here, and this is an estimate of the wet solidus, the best we could do back then. We have better estimates now. Anyway, so along a 1600K AdBat, you cross the solidus, you produce this melting, and you make oceanic crust, right? One of the questions that's been around for a while is the low velocity zone partially molten? And if it is, that could be a very interesting constraint on the geotherm. What we concluded from this analysis is that as long as the oceanic lithosphere is older than about 5 million years, the answer is no, it's not going to be partially molten. The low velocity zone is just way too cold to be partially molten. You might get a little bit of hydrous, very water-rich fluid, but even if as you go beyond 50 million years, you're beyond even the wet solidus. Mark Hirschman has done a better analysis of this with better experimental constraints on the wet solidus and also the carbonated solidus. And what he finds is that you can get in the low velocity zone, so this is now lithospheric age versus depth, so you can get a little bit of melt in the low velocity zone, but less than 0.1%. And not enough to really affect seismic observations. So very tiny amounts, a little bit of carbonated melt as well. And this may, in fact, be very mobile and rush to the surface, but very, very little melt down there. Let me turn now to the bottom thermal boundary layer. The lower thermal boundary layer got a big boost from the discovery of post-perovskite in the lab and also from seismic observations of not only reflectors at the very base of the mantle, but double reflectors at the base of the mantle. So very interesting observation. And John Herlin, I think, in this paper, they were the first to propose an explanation for these doubled reflectors. The idea is that you have a transition from perovskite to post-perovskite here in the dashed line, and it intersects mantle geotherms in a potentially very interesting way. So if you look at this warm geotherm here, you see that it crosses this transition twice, once there and once there. And because post-perovskite is faster than perovskite, what you get along this warm geotherm is an increase in seismic wave velocity there and then you're in the post-perovskite stability field, and then back to perovskite there, and the velocity goes back down again. So double reflectors. And you can turn that around then and use observations of double reflectors as a constraint on the geotherm. An interesting idea. I think the community is still still an interesting avenue of research. I think it's become a little bit more complicated with time. One of the observations that's made it more complicated is that this perovskite to post-perovskite transition appears to be very, very broad. This is some data for pyrolite. Dan Shim has also obtained results that show a similar width to the perovskite to post-perovskite transition. This is not going to reflect anything. So I think it's an open question, actually. What produces those deep lower mantle reflectors? This particular paper suggests one possibility, and that is that the material in which the reflectors are seen is not pyrolite, but actually something more like Hartsbergite, depleted material. This is actually just pure olivine here. And in pure olivine, the transition is narrow enough to reflect things, so maybe that's the answer. There are other transitions down there. There's a transition in silica that may be playing some role as well.
Is that thickness of the transition related to iron-magnesium, mixed phase region?
It is, yes. It's related to the iron-magnesium partitioning and also aluminum partitioning between the two different phases, yes. And that's one reason that these guys say it's quite a bit wider in pyrolite because of the aluminum partitioning, which of course you don't have in the olivine. Another way to look at that bottom thermal boundary layer might be from heat flow. This is an analysis that we did where we took this simple boundary layer analysis from the 70s, Richter and McKenzie, or either one of those. And anyway, you get a relationship between heat flow, between the temperature contrast across the bottom thermal boundary layer, and the thickness of that bottom thermal boundary layer. And we took our first principles calculations of the thermal conductivity of perovskite to map out, as a function of heat flow, what the temperature contrast across that bottom boundary layer might be, okay, on this axis, and the thickness of the boundary layer. And there are some constraints here on what that heat flow out of the core might be. This is from plume flux. This is a sort of venerable exercise in the geophysics literature that goes all the way back to Jeff Davies and probably beyond. And the idea is you can estimate how much heat is coming out of plumes. You assume that those plumes originate at the core mantle boundary, and you get your constraint on core heat flux. Great. One of the problems, one of the sort of twists in that story over the years is that fanning out of AdBats that I showed in the first slide. That tends to change your estimate of core heat flux versus plume heat flux, and also the fact that not all plumes make it to the surface. So that places sort of a lower bound on the heat flux, and core conduction, I'll say a little bit more about that, might place an upper bound on it. Okay, what other constraints do we have on that lower thermal boundary layer? Maybe we can say something about the total temperature contrast and the thickness of it. What about the temperature itself? What about the temperature at the core mantle boundary, 4,000 degrees, 4,100 K in this particular version that I plotted here? That constraint comes from the core side, okay? And from the core side, what you need to know, first of all, is the melting point of iron. Jackie showed this figure from this paper already. Here's the data. They go up to 200 GPa. It's a very nice technique where they do X-ray diffraction, and they have positive identification of melt from the X-ray diffraction from diffuse scattering. Very nice, nicely done. And they show this melting curve, which is consistent with the Brown and McQueen shockwave points, and also very nicely consistent with this ab initio melting curve, which is this small dashed line here. This is not an ab initio melting curve, even though they say it is. It's not. It's just a peripotential. This is, and it agrees nicely with that. So I think we know the iron melting curve pretty well, actually, now. I think Another nice thing they did in this study is that this is the old, some of you may be familiar with the melting curve of Reine Bowler, where he identifies melting as a change in sort of the apparent motion of the material. What these guys notice is that they still had X-ray diffraction above this point, but what they saw is that they get rapid recrystallization happening along this line here at a temperature pressure condition that agrees very well with what Reine Bowler's identified as melting. So what Reine Bowler identified as melting is probably not melting, it's probably just this onset of rapid recrystallization. So that sort of explains that discrepancy. The core isn't pure iron, there's some light elements in it. One of the nicest analyses, I think, of light elements in the core is this study of Alfé. What they did is they looked at the effect of silicon, oxygen, sulfur on the density of the liquid. They calculated the partition coefficient between liquid and solid, and that gives them how much of these guys are in the solid, and they compare that to the density jump determined seismologically. And that gives them a total amount of pairs of silicon oxygen or sulfur oxygen that can explain the density jump. And they also calculate the freezing point depression, turns out to be 700 Kelvin. So putting all this together, you get some constraint on the temperature at the inner core boundary. And we know something about the adiabatic gradient in the outer core, so you can extrapolate upward to the core mantle boundary, and you end up with something like 4,000 degrees. And that's what that's based on. The core, there's a new twist to our understanding of the core, which has come from new ab initio calculations of the thermal conductivity of iron at core conditions, and also some subsequent experimental measurements, one set of which agrees very nicely with this prediction, and another set which disagrees, completely. But anyway, this is if the thermal conductivity in the core is really this high, this is much higher than we thought before, then our picture of the dynamics of the outer core might be very, very different. In order for something to convect, the heat transported by convection has to be greater than the heat transported down the adiabat by conduction. Okay? And this conductivity is so high that it may actually shut off convection in parts of the outer core. What these guys estimate is that you might have a stably stratified layer at the top of the outer core, and that obviously changes the temperature distribution in the core. The same comments I made before about the Bullen inhomogeneity parameter apply to the core as well. In Prem, the Bullen inhomogeneity parameter is 1 throughout the outer core, indicating adiabaticity, but variations by a few percent are, I think, probably permitted by the observations. Yes?
Do you envision any impact from light element for that thermal conductivity measurements, or is it so small that it's not going to impact?
They looked at that, actually. So what these three curves are, so black is pure iron, red is for a silicon-oxygen mixture, and blue is for a sulfur-oxygen mixture. So it's still high. Yes?
What's the status of radiogenic elements in the core?
Yeah. So whether they're there or not, we don't know. There's no observational basis for knowing. This creates a bit of a catastrophe in our understanding of how the geodynamo is produced, potentially, because the outer core has to convect to produce a dynamo. And it has to produce a dynamo for 4 billion years, not just for the last billion years where the inner core was around. And so the idea of radioactivity in the outer core is still very much alive. I think these days mostly motivated by trying to get the core to convect and trying to produce a field, and the difficulty in imagining sort of other ways that might be done. What will be nice, of course, is some experimental data that tell us about partitioning of potassium, uranium, and thorium, etc., between silicates and iron at a megabar or so. Just a few words about the inner core. The idea of inner core convection has been around for a while. The same group calculated the thermal conductivity of solid iron and found it to be even higher. That very high conductivity makes it very difficult for the inner core to convect, actually. I think this is probably unlikely because the conductivity is so high and so efficient. It makes it so efficient at transporting heat by conduction alone. Although the inner core might still be interesting, that doesn't necessarily mean that it's static. I mean, this is one proposal that was made recently by Dave Gubbins, based on looking at lateral variations in heat flow at the core mantle boundary, which can be very, very large, 100%. And you might even get downwelling regions in the outer core and upwelling regions in the outer core. And these may cause lateral variations in the growth rate of the inner core, which could cause internal mass rearrangements. So there might be interesting things going on in the inner core, but it's probably not the sort of standard thermal convection that we usually think about. I'll stop there. Thanks.
So to follow up on the last things you just said, Lars, in the end, though, we expect the inner core and the outer core to be close to adiabatic, right? Regardless of whether it's convecting or funny things are going on, because
Yes.
temperature variations will be modest.
Yeah, that's right. Yeah, so that means that across the inner core, something like 200 Kelvin.
Other questions? Our next speaker is Alex. Maybe I want to ask you a question about what would be, in your view, the most urgent or needed nuclear physics constraint at this moment? Because I got the impression that we are doing quite well. We kind of know most things.
Well, something I'm particularly interested in is melting at the base of the mantle. I think that's an interesting question. There have been, as you showed, several different experimental and theoretical versions of the melting curve in the deep mantle published. They don't all agree with each other. It matters not only what the temperature is at the base, but also how curved this thing is, because that determines whether the magma ocean starts crystallizing from the middle or from the base. So that's an important thing. Looking at I think this too is fascinating to me. This sort of thing. This is fascinating. Looking at this, looking at how the potential temperature has changed with time, looking at how good the petrologic constraints are on that, looking from the geodynamical point of view on to what extent can we understand this. Many of the more sort of venerable thermal evolution models from the geodynamical perspective would have predicted something more like this, something curving up like this, and that's not seen in the petrology. And so, what is going on? Is it the more difficult, the greater difficulty of subduction in the past, as suggested by this Korinaga model, or is it something else?
Lars, can you explain that curvature downwards beyond 3 billion years?
No. Sorry.
It's a model.
Yeah.
Yeah. So
What causes it in the model?
Well, the model uses the thicker. Okay, so the early Earth, you have a hotter mantle. It makes a thicker crust that makes it harder to subduct. On top of that, the extensive melting will dehydrate the lithosphere, making it harder to bend. So the Korinaga model uses those two effects to have a relationship where convective efficiency increases when it gets a little bit hotter, but when it gets too hot, the convective efficiency decreases.
Mm-hmm. Right.
And that is not universally low.
Right.
It's like stagnant.
Yeah. Right.
But Torsten, your explanation isn't consistent with those curves, right? Because at 4 billion years, the mantle is colder, so the lithosphere should be thinner. Right? So there's an additional piece of physics in there.
I think that's the physics.
No,
But that's not consistent with the curve.
what he has
It should be.
is thicker because he
We have another question here. Yes.
Yeah. So, one of the I say main parameters when you do calculations of geotherms, right, is try to define or decide which is the foot temperature or the temperature that you anchored, to do these calculations. Typically, people go for the Browning-Shanklin, for instance, for the lower mantle. Do you think that's a good way, approach, or that's a good temperature to do these sorts of calculations, or what would be the temperature for?
Right. So there are two questions. One is the choice of the foot temperature or the potential temperature, and I would argue that melting at mid-ocean ridges is the best constraint on that. The other question is, once you've decided on a potential temperature, what does the rest of the AdBat look like? And I think something based on experimental data of physical properties of minerals, which is what we've done here, not that we've done it the best possible way, but something based on that is probably the best way to go now. At the time that Brown and Shanklin did their study, they used only seismological data, to derive the adiabatic gradient. And that involves various approximations. For example, what they did was they took the seismic wave velocities, they related that to a Debye temperature, they related the pressure dependence of the Debye temperature to, finally, the Gruneisen parameter. So it's kind of a roundabout way to go, but it was a good thing to do back when they did it because we didn't know very much experimentally about material properties. We know a lot more now.
So you think that the way to go is just to anchor, know what's the initial temperature from the surface rather than, for instance, because people argue that there's, this dissociation temperature at which olivine dissociates into Bridgman and ferropericlase. That's the argument. But
yeah, there are other constraints on the depth of the 410, for example, the depth of the 660. The 1600 Kelvin adiabat is consistent with that. But I think melting at the surface is the best constraint on the potential temperature.
So we have opportunity to continue the discussion later on. There's a general discussion part at the end of the morning session. So let's move on. Before we do that, let's thank Lars for such an excellent review. So next one, we're going to have Cindy Lee to give us a blackboard review from a geochemical point of view.